Okay, good morning. So we will continue with the theory of fire propagation, the fire dynamics course. So we have seen 5 modules so far, the basics, then the review of thermochemistry, chemical equilibrium and kinetics, then a review of premix and diffusion flames. Then we saw the ignition, flame spread and mass burning characteristics of liquid fuels, and again the burning of solid fuel module, which covered the same aspects like ignition, flame spread and the burning rate. So we also saw some theoretical analysis as well as the correlations which was dependent on the experiments. Now we will move on to analysis of fire plumes. So once the fire is set up, you know that there will be hot gases which are generated. Some soot particles also can be released from the fire, so that we have a smoke which is coming out of the fire, and the transport of the smoke is basically analyzed in this particular chapter. How the fire plume is formed first. Okay, there is a combustion zone and there will be some oscillatory zone. Then the hot gases without much reactions will propagate, and due to buoyancy, you will see that these hot gases rise up, and this analysis becomes very important when you have a fire within a compartment. So within a compartment, if you have a fire, based upon the size of the fire, you will see that the hot gases are formed, the smoke is formed, and the smoke actually rises up and hits the ceiling and actually spreads over the ceiling and descend down, etc. So a lot of dynamics are there for this. So to analyze the strength of the hot gases which are rising up, we need to understand what is a fire plume and how the characteristics of the fire plume are defined. So for example, based upon the strength of the fire, the buoyancy driven gas flow, the hot gas flow will be much stronger. So if the fire itself is not so big, then the plume will be weak. So in order to detect the fire, so you put sensors at the ceiling, etc. So how fast the plume is transported towards the sensor, that will be the important factor for detecting the fire as soon as possible. So stronger fires can be detected sooner. So the analysis of fire plume includes first the understanding of the fire plume, which is the vertical rise up of the hot gas. Then after it hits the ceiling, basically within an enclosure, how it spreads as ceiling jet, that is also covered in this particular module. Now let us consider a jet diffusion flame from a gaseous fuel. So for example, there is a burner or a simple pipe through which a gaseous fuel is supplied, fuel gas is supplied. Now we know that upon ignition a diffusion flame is formed over this particular burner. The extent of this flame, which is the flame height HF, that depends upon the momentum of the gas jet as well as the buoyancy forces, because you can see that the gravity acts in the vertically downward direction, and this causes a air flow which is in the upward direction. So this flame is subjected to entrainment of the air from the ambient, and the hot gas rise up, the recirculatory natural convection flow will occur. So the buoyancy forces of various degrees are expected, and these buoyancy forces are caused by density differences. Okay, so now this is for the gaseous fuel. Here predominantly there is a given momentum. So for example, if u is the exit velocity of this gas, average exit velocity of the gaseous fuel, then it has a momentum of rho u square. Right? So there is a momentum, then there is a buoyancy force. So both of them aid the height of the fire. But if you take the fire established over condensed fuel, like solid fuel or a liquid fuel, then you have a condensed fuel surface and a fire is established over this. Now, if you see the fuel vapor in the case of liquid or fuel gases in the case of solid, which are coming out of the surface, condensed fuel surface, they will not have much momentum. So, U will be much lesser than, so I will say U for the condensed fuel, UC will be much less than U, which is the fuel gas which is injected at a particular velocity. So, this fire, the extent of this fire which is established over a condensed fuel surface is dependent on buoyancy forces. Basically, the momentum is very less. So, that is the basic difference between a gaseous jet diffusion flame and the flame which is established over the condensed fuel. The momentum is very low. The mass coming out of the condensed fuel surface will not have a big velocity. So, the buoyancy forces are caused in both the cases, which are due to density differences. So, if you take this particular flame, so I will try to draw the temperature profile. The temperature is lower in this portion, it increases to a maximum value and reduces to the ambient temperature asymptotically. So, you can see there is a good temperature variation. This is T versus the radius, for example. So, if this is a circular base here. So, you can see that at the flame zone you reach the maximum temperature and the temperature decreases towards the ambient and reaches the ambient temperature asymptotically. So, this steep temperature gradient, the steep temperature gradient causes density gradient, because you know the equation of state PV equal to RT. We can say PV specific volume, P is pressure in Pascal, V is specific volume, R is the specific gas constant, T is temperature in Kelvin. Now, I can write this as P equal to 1 by V RT or P equal to rho density RT. So, now you can see that for say this fire is a fire, the temperature variation will be very steep, but the pressure variation will not be so high. So, we can say that the pressure can be, see for example, due to the flow there will be some pressure variation, dynamic pressure variation, but the atmospheric pressure is about 1 bar. So, the pressure fluctuations will be over that, say for example, it may be 1 bar, 1.1 bar, something like that. So, we can say the pressure remains almost constant, the specific gas constant also remains almost the same. So, we can say that the density goes inversely as temperature. That means, if you have a steep temperature gradient, it will also cause a steep density gradient, and this is what is triggering the buoyancy aided flow. Do you understand? So, what happens is, if you draw this flame again and if you try to draw the velocity vector, you can see that the velocity will be increasing and again decreases to 0 like this. So, this will be a typical velocity vector across the flame. So, that is a very high velocity. This high velocity which is coming, this is due to the buoyancy driven flow. So, as a consequence of steep density gradient, you can see that hot gases rise upwards, because hot gases are at lower density. So, it actually rise up and the cold gas or the cold air from the atmosphere comes to its place. That causes the flow, buoyancy driven flow. Now, the relatively lower density which is caused by higher temperature, that makes the gas to rise up. Do you understand? So, this buoyancy driven flow which is established over the fire is called fire plume. Okay. So, the hot gases which are rising up, in some part of this basically there will be some chemical reaction which will taking place, but predominantly the gases are going to rise up to a very large height, and after a small height from the base of the fuel, you will see that there will be no big chemical reactions also taking place. So, these hot products are just going to rise up, and such a flow of hot gases which is established over the fire, that is termed as fire plume. So, basically fire plume can be taken as non-reactive flow of hot gases which are actually aided by the buoyancy forces. Do you understand? So, the buoyancy forces cause this fire plume to go over the fire in the upward direction. Now, if you take the case of say vertical plate, so let us take a case of vertical plate which is at a higher temperature than the ambient. So, TH, ambient temperature may be at TC. So, now you know that there is a natural convection which is going to be produced here. For example, the hot near the hot plate, the fluid which is in contact with the hot surface will be having higher temperature, so lower density, so it rises up, and the air or the fluid from the ambient comes in. So, basically this causes a temperature and temperature gradient from the surface to the ambient. Also, it causes the velocity which is induced. So, the velocity which is induced here will be like this. So, you will have some maximum velocity at a particular this, and it goes to 0. So, now at the edge of the boundary layer actually grows like this. At the edge of the boundary layer, velocity goes to 0 in a natural convective flow because there is no force flow. So, within the boundary layer there is a the velocity profile looks like this. The velocity increases, reaches a maximum, then decreases to a asymptotic towards 0 in the boundary layer edge. So, this boundary layer, based upon the length of this vertical plate, initially will be laminar. Then if the length is very high, okay, then the flow transitions towards the turbulent flow and becomes fully turbulent. So, this is the case of a hot plate. Similarly, if you take flame can be also viewed as a hot surface which is actually vertically oriented. So, here also the plume basically starts as a laminar plume, and as the height increases it becomes turbulent. Do you understand? So, however, one more point here is, here also if you take the vertical hot plate case, based upon the temperature difference TH minus TC, the strength of the convection, natural convection will be higher or lower. Similarly, here also the transition from laminar to turbulent etc. depends upon the strength and the dimension of the fire. Okay, the fire, even it may be a smaller dimension, but it burns at a higher rate. The fuel burns at a higher rate, the heat release rate is higher. In such a case, the plume will be stronger. It becomes turbulent after a particular height sooner. Now, based upon the dimension of, say, if the diameter of the say liquid pool for example is higher, then it will cause turbulent plume and so on. So, the fire plume is an important feature of a fire which is the buoyancy driven flow established over the fire, and which is dependent on the strength and dimension of the fire. The fire plume initially can be laminar, but it transitions towards the turbulent. We will see some characteristics of fire plume now. So, we have already discussed that the buoyancy forces depends upon the temperature gradient. However, if the temperature gradient which causes the density gradient reduces, temperature gradient may be very high near the flame zone, but if you go to the plume zone, the temperature gradient decreases. So, for example, I have a source, there is a fire, and the hot gases are rising up. So, if you go to some particular height, you can see that the temperature gradient may not be so high. Here the temperature gradient will be very high, like what we have drawn like this. But in this case, the temperature gradient may not be so high. If you go to this particular height and try to draw it, the temperature gradient may be smaller. Okay, so as the temperature gradient decreases, you can see that the density gradient or the density differences also will be smaller. That means the buoyancy force which triggers the plume rise up will also be reduced. Okay. So, that means as we go from the base of the fuel towards higher heights, you will see that the temperature and velocity variations will be significantly affected. So, temperature and velocity variations are the profiles as a function of height in a fire flume is very important characteristic which we want to analyze. Now, the hot gas rise upwards, cold atmospheric air, the cold atmospheric air and the other gases entrain into the fire plume. This entrainment rate is the future. Okay. So, first what we want to analyze is the temperature and velocity variations as a function of height in a fire flume. Okay. Now, the second aspect is the entrainment of the ambient gases including the air into the plume. So, we have to understand certain things in this. So, the entrainment basically occurs due to viscosity of the fluid. In the laminar, it is molecular, the viscosity which is actually controlling the fluid property which controls the entrainment. But if you go to turbulent flow, it is the action of eddies which controls this. Okay. Now, this aspect of entrainment of gas, ambient gas or ambient air into the plume is a important characteristic for this. Again, we can say that as a function of height, similar to how the temperature and velocity variations are seen, the entrainment also will be dependent on height, that we can easily see. So, now if you take let us take a case of a gas jet coming out of a circular paper or nozzle, whatever it may be, then you will see that there is a length from the exit of the pipe or nozzle which is called potential core. Then, so let us say the velocity of this gas jet at the exit of the nozzle is ue, then this gas jet has a momentum of u rho into ue square. Okay, now what happens is, as the jet is injected out of this, gas jet is injected out of this, then the atmospheric air entrains into this. So, the jet actually spreads. If this gas is injected in an open environment or without any confinement, then the momentum is conserved. So, for example, if you take the momentum of the jet at every plane, you will see that the momentum will be the same. Momentum is conserved. Okay. Now, what happens to the velocity? If you take the central line of the jet, the velocity of the central line basically can be plotted. So, I will say UO, center line velocity versus height. Height is Z here and this is radius R. So, this remains constant in the potential core region and then decreases. So, this is called velocity decay. So, you will see that the velocity of the jet decreases as a function of height, but momentum remains constant because the mass is added at every plane. So, since mass is added, even though velocity decreases, the momentum is conserved. So, this is isothermal jet. See, for example, I am talking about a gas which is at a low temperature. Maybe it has same density as air also. So, in this case, this simple analysis is available in literature. But if you go for, say, a flame which is coming out of a solid surface or a nozzle, then you will see that the entrainment characteristics will be entirely different, because now you can see that the buoyancy driven flow accelerates this gas. The pressure variations are dictated by this buoyancy driven flow, and due to that also you will see that the air entrainment occurs. So, in the fire zone maximum air entrainment occurs, and when you go to different heights, then you will see that the entrainment rate reduces. So, the important characteristics of fire plume are the temperature and velocity variations that will signify the strength of the fire plume. Then you go to the entrainment rate of the ambient air and the gases inside this. So, in the case of laminar flows, it is due to fluid friction the entrainment occurs. In the case of turbulent flow, it is due to the action of eddies of different scales. Okay. So, this is the important things which you will understand. So, now as I told you, the flame itself, the fire itself, when it is turbulent, it is very oscillatory. That means the eddy dynamics will dictate the fire plume also. The fire plume will also be dependent on the eddy dynamics, the characteristics of this. So, anyway, as we do statistical analysis in a turbulent flow, like average velocity, average temperature, average density, etc., which is taken as a time averaged value. Similar to this, we can also analyze the plume here. Okay. So, the strength of the plume depends on the fire dimension and its strength, the rate of burning, etc. And as we go from the fire base to different heights, then we will see that the density differences decrease, and due to which the buoyancy forces also decrease. And now we have to categorize the plume as a stronger plume or a weaker plume based upon the analysis of the temperature and velocity variations and the entrainment rate of the ambient air and the gas. Now, this zones of fire plume will be discussed here. Here, as per Quantry in 2017 and Esges in 1995, this is a typical picture or schematic showing the zones in a fire plume. So, let us say this is the base of the fire. A fire is established here, and air entrainment comes from the ambient. You can see that a visible flame is seen up to a certain height, and after this height there is a zone called intermittent zone where the flame actually oscillates. So, one time instant the flame can be within this zone, another time instant the flame can go to this zone. That is all. It cannot cross this height, the intermittent zone, it cannot cross this height. The flame can oscillate well within these two heights. That is what we categorize as the flame zone. This is a particular height here, flame zone height, and the intermittent height. The flame oscillates between these two. Now, you can see that the flame is always seen in the flame zone. Always it is there, the flame zone. But in intermittent zone, at a particular time instant, it may be at this point, it may grow till this point, or at another time instant, it may grow to this point. So, that means in the intermittent zone, we will not be able to see the flame at every location always, because of the fact that the flame actually oscillates up and down, and within the flame zone always the flame is seen. So, you can say we can use any optical method or say temperature probing, etc., to understand the height where the flame is always present. After that, the flame will be oscillating basically. So, what is the maximum height the flame grows to? So, if you track the flame for enough time period, then you can note what is the maximum height the visible flame is seen. So, that is actually taken as the intermittent zone height, and the flame zone is the one where the flame is always seen. That means there is no time instant where the flame is not present in this zone. In the intermittent zone, flame may be present at a particular time instant at a particular location, or it may not be. So, now based upon this I get a average flame height. This is the average flame height. So, this average flame height basically signifies the location where the flame is seen at least 50% of the time period of probing. So, if you take, say, I do the probing for about 100 seconds. In this location, at least 50% of the time, 50 seconds at least, the flame is seen. So, above this height, it is not seen for 50 seconds, it is seen for only lesser than 50 seconds. Below this height, it may be seen for more than 50 seconds, but below this flame zone height, it is seen for 100 seconds. So, that is the first two zones where the chemical reactions or the visible flame is seen for 100% of the time, categorized as the flame zone. The intermediate zone is one in which flame is seen, but it is not seen always, and it actually takes into account of the maximum flame height which is visibly seen. Then after this, the flame is never seen, only hot gas rise up. So, after this zone, only hot gases rise up. So, that zone, as I told previously, the zone of hot gases over the flame is called the plume zone. Okay. You can see that the air entrainment from the ambient or the gases entrainment from the ambient always occurs at several heights. It is very stronger in the entrainment is very strong in the flame zone, and in the plume zone the entrainment decreases because of the fact that the temperature etc. decreases as you go up. So, now this is the axial distance, Z is the axial distance and lateral is the perpendicular to that. So, now let us plot as a function of Z two quantities. One is the center line velocity, that is, if this is the center line or axis, this we can say radius. If you say if it is a circular source, then I can say radius equal to 0 at the center line. So, u naught corresponds to the center line velocity. Similarly, T naught corresponds to center line temperature, but delta T naught is center line temperature minus the ambient temperature. Okay. So, that is temperature difference. So, we are trying to plot center line velocity versus Z, center line temperature T naught minus T infinity versus Z. So, let us see the center line velocity first. So, now at the base, so this is base, so where I can say that Z equal to 0. So, base is called Z equal to 0. So, now if I extrapolate this, basically I will get some value for u naught, very low value. From the surface, fuel gases are getting out. This is a condensed fuel surface. Okay. So, fuel gases are getting out. So, I have a very low velocity at Z equal to 0 and the velocity increases, and you can see this is the flame zone, flame height. At the near to the flame zone, the velocity reaches the maximum value. Then after that, the velocity slowly decreases. So, there is a decay, small decay in the velocity, and it just becomes almost constant after a particular height. There is no influence after that, there is no growth, or it becomes constant, center velocity becomes almost constant, or it may decrease further also. So, you can see that this velocity increases because of the buoyancy driven force at the tip of the flame, and it actually has the maximum value there, then it actually decreases. So, this is about the center line velocity. So, in a pure jet we have seen that the velocity decays, but in this case you can see that the velocity increases because of the flame here and reaches the maximum, then it decreases. Now, coming to the temperature difference. In the flame zone, the average temperature, see the center line temperature, like say some potential cohesion or something like that we can take, where the temperature difference will not much vary. Okay, basically there will be some variation, some decrease basically, but we can say that it is we can say this is almost same, like this it will be temperature difference. So, now this temperature in the flame zone, the variation is not much, so we just plot like this. But after reaching the flame particular this flame zone height here, you will see a decrease in the center line temperature, okay, because of the heat transfer or heat loss, etc., and also no heat generation due to chemical reaction. So, now after the intermittent zone, you can see that there is so this is the average flame height. After the average flame height, the decrease continues, and after the intermittent zone, it slowly decreases and asymptotically reaches a constant value. This is about the temperature difference. So, we have seen the variation. This is not lateral variation, please understand, this is the axial variation of the center line velocity, the velocity at the center line. Similarly, the axial variation of the temperature, we have seen both. Now, coming to the radial variation or lateral variation, okay, let us say this is the lateral variation. The plume velocity, let us take u. At center line velocity, this is u naught at the particular z. So, this is the z. So, particular z, u naught will be the value of the center line velocity, and it decreases to a 0 value at the edge of the plume. This is the edge of the plume. The dashed line shows the plume edge. So, towards the edge of the plume, you will see that the velocity goes to 0 value, and it is maximum at this, and this is called Gaussian profile. Typical profile of the velocity. Do you understand? So, this is the variation in the lateral direction or radius, with respect to radius. Okay, so this u decays like this, the u naught decays like this after a particular this. We are not interested in this region, we are interested only in this region. This is the plume region. So, based upon this strength and activities here, the plume region, the velocity variation, temperature variation, etc., are important for us. And at every region, the typical profiles of temperature velocity will be like this. Temperature on the other hand also will be maximum here, same type of profile it will display. So, it will asymptotically go to a ambient value like this. So, this will be the temperature profile also in the plume region. So, our analysis will help us to get the u naught, t naught as a function of z, as well as u as a function of r, or this is the, say let us say this is radial direction, u as a function of r, t as a function of r at different, at any z, I can say any location, actual location. So, this is the characteristics, base characteristic of the fire plume.